This is session 8 for Models in Epidemiology and Biostatistics. I'm Gordon Hilton-Fick. Today's session covering many issues related to how the models we've been considering handle exposure. So far, we've looked at just a single dichotomous exposure. And we've also seen circumstances then where the model includes potential confounder modifiers of that disease exposure relationship. Well, I'd like to now take some time and discuss the circumstance in which the exposure is measured. We'll also look at a circumstance in which there are two dichotomous exposures and exposures with more than two levels. Then we will be looking at a circumstance in which we have two explanatory variables that are both measured. And that will lead us to some interesting notions. We'll be looking at something called a saddle, and we'll have a notion that is new, and that is the notion of a crossing. And then it is my plan to include in this session several illustrations, two of them from the outstanding book on case control studies by Breslow and Day, and more on that when we come to it. Let's now begin. So let's take along a situation in which we have a exposure that is measured and possibly an explanatory variable that's measured. And we'll see in this section that this gives us many of the same issues we've seen before. However, the complexity changes pretty fast. So, for starts, and indeed for all of this session, pretty much all of this session, we're going to suppose that we have a linearity assumption, so that the log of odds of disease varies linearly with age and also that it varies linearly with exposure. In the last session, we saw that, the linearity assumption is often not present, and many, and if indeed all of the issues that we'll be discussing here can be extended to nonlinear situations. Okay, now let's look at a model that we have seen quite a bit of since we began our exploration of models in epidemiology and biostatistics. And we'll then use the notion of the probability of disease and the conditional probabilities given exposure, given gender, given age. And what we saw was a model that might look like this one with 8 terms. At least that could be the place we would want to start. We've looked at this from various perspectives already, where we have dichotomous age, just gender, male-female, and dichotomous exposure. Well, now let's think of this from the point of view of the characteristics age and exposure being measured. All right. If we were to simply take the equation and re-express the right-hand side in a slightly different way, where we then have the log of odds of disease as a line in exposure, a line that has varying intercepts, all of these pieces then become the intercepts with various combinations of gender and specified age. Similarly, we would also have varying slopes in this disease exposure relationship. All of these things now, the beta 4 to beta 7 and their corresponding terms, then giving us differing slopes depending on gender and depending on the specification of age. So you can see that, well, we can see now that we are writing our investigation into the disease exposure relationship not as a single odds ratio, but now a collection of possible slopes reflecting the extent to which exposure, a measured variable, impacts on the log of the odds of disease. And we can continue with further expression of this by grouping terms that may help in your interpretation. For example, we can see that this set of terms then can be viewed as the slope for the log of the odds of disease as a function of age for a specified value of exposure. Okay, so we can do that. We can also think about the impact of age on the slope here now, insofar as we're viewing the log of the odds of disease as a function of exposure, and how it is that the slope in this equation impacts on this slope. Okay, so now we've got slopes. We've got lots of them. We've got lots of rates of change of log of odds of disease per unit change in something. Okay. So let's take a look at this a little bit more. We can see that the slope that we have, that was the coefficient of exposure here, involves another slope. That is the rate of change now of something we need to understand per unit change in age. Right, so viewing this as a function of age, we again get a line. And so the rate of change of the slope per year of age from the coefficient of A for this line gives us this expression, trying to make things and get things that are steadily more simple and simpler and simpler. Okay, so not too surprisingly, you can see then that if we begin our investigation, which would be the most typical one, I guess, of an exploration of the test of significance for beta 7 being 0, if it's not 0, then we get that gender modifies the age modification, in that the rate of change of this slope depends on gender. Aha! So you can see we've got slopes of slopes. And there are many other scenarios that we could explore in exactly the same way, perhaps starting with beta 7 equals 0, if in fact there's no evidence of that form of modification written just above. Okay, so that gives us a whole wide range of models, starting with that model with 8 terms, and then specializing it possibly depending on circumstances. So much of what we saw in the earlier sessions can be implemented. All of the issues in model construction could be used in those settings. All right, let's now take the second type of way in which we may wish to study exposure. Let's now imagine that we have 2 exposures, and they're both, for the moment, we'll suppose, just dichotomous. Okay? Then we get a collection of probabilities, or log odds, expressed in terms of the 4 combinations of exposure. We have those exposed to E1 and those exposed to E2. So For example, the group that have no exposures would be where E1 and E2 are both 0. But you can see now again that there are the 4 combinations, where we could have a collection of individuals that are subject to both exposures. And further, we can see then that we have now 2 exposures worthy of study, and those are then themselves functions of or possibly dependent on the 2 potential modifier confounders, that is age and gender, as before. And now what we come to is a circumstance in which in the literature we really do want to use the word interaction. It's the most widely seen, going back to the very early work of R.A. Fisher. So we now wish to assess the 2 exposures, and we would typically begin with the study of the possibility of interaction between the 2 exposures. Okay. And this again goes back to the very earliest of writings from R.A. Fisher, that it makes no sense to study the 2 exposures separately if indeed there is the possibility of an interaction of exposures. Okay. So now we've got questions that might be of interest to the investigator. Does the disease exposure 1 relationship depend on the presence or absence of exposure 2? And we can think of that symmetrically. Does the disease exposure 2 relationship depend on the presence or absence of exposure 1? And then again, we have that particular, now admittedly starting to get more complicated, disease exposure 1, exposure 2 relationship. How are those relationships modified by age and or gender? And then if there is no modification of this curious form, is it possible then that such an interaction could be confounded by age and or gender? Okay, so it would be the same as before. If we rule out interaction, if we rule out modification insofar as how it impacts on interaction, then we can explore whether or not that particular interaction is confounded by age or gender. Okay. So inevitably then, and this goes back to something we touched on much earlier, we are interested in the study of this complicated expression, which is now a difference between 2 differences. We have the log odds ratio, exposure 1, in the presence of exposure 2, and the log odds ratio, exposure 1, in the absence of exposure 2. But there's a symmetry here. In other words, that expression is the same as the log odds ratio for exposure 2 in the presence of exposure 1 minus the log odds ratio exposure 2 in the absence of exposure 1. That's an attractive feature, isn't it? That this expression, this is now discussing the difference between the 2 differences, keying one's attention on exposure 1, can be done so with exposure 2, and this is the common expression. You'll notice the coefficients of this expression in these 4 log odds are 1, minus 1, minus 1, 1. And, well, it turns out that could take us, not in this session and not for the foreseeable future, but a whole range of issues discussed by Fisher in his very earliest works and on this topic in relation to the use of the theory of groups. Unbelievable. Yep. These coefficients then become important in that issue. All right, but I'm off topic. More to the crucial issue is, how do I study interaction? Well, there's a little bit of frankly, just details to sort out. How do we do this? How do we capture this particular difference between two differences? Okay. Well, it turns out that we can do so with this model. Now, again, I'm going to be maybe leaving some of the more technical parts of this out of discussion right now, except for the fact that it should look pretty sensible. What are we going to have? We're going to have terms that involve the product of the two exposures. Then we're going to have terms involving just exposure 1, just exposure 2, and then terms that don't involve either exposure 1 or exposure 2. It's getting more complicated. It's certainly true. Now we have a model with 16 terms. Wow. But a little bit of consideration would help you to see that, in fact, all of this is now available to us by specialization of this model to various cases. Okay? Now, it turns out then that with a little bit of the math that we're going to skip here, it can be shown that that last coefficient of the product of the two exposures is what gives us the ability to see interaction and the extent to which the interaction is either modified and or confounded by age and gender. Okay? Because we get these expressions. We get, for example, the ability to study this expression for the males, that's specializing this, and this expression for the females, and then the study of that difference, capturing how gender impacts on this issue of interaction and the extent to which gender impacts on that. Now, there's quite a bit going on here. This is one of those places where it can be very helpful to you, the listener, follower of this video, could with considerable advantage take this complicated model with 16 terms and write out some of the other forms of specialization, as we've done in previous sessions. It can really help ground you to understanding what is admittedly a not straightforward set of circumstances. Okay. And there's then, most crucially for us, the ability to interpret the various regression coefficients. And not too surprisingly, if in fact that very last term, that's beta 15 there, right? Because they range from beta 0 up to beta 15. If in fact it's not 0, then we have it, in a sense, the most complicated set of circumstances. So we see then that we have the ability to study interaction and the extent to which interaction may be modified by potential confounder modifiers. Okay. We come to the study of how the two exposures are involved, and all of this is about understanding whether or not there's an interaction between these exposures, which can be, again, the most crucial thing to know. And there are many circumstances here. Okay. Further, we can see that there are models that detail only the issues of confounding. In other words, if we take that complicated expression with the 16 terms and rule out all the terms that deal with modification, then we're left with issues concerning confounding. And in particular, it is our study of, in this instance, beta 12 here, which is the coefficient of the product of the two exposures, that we would wish to explore. This is a confounding issue now, depending on the possible values of beta 1, beta 2, and beta 3. The extent to which those three things are varied, we can then explore the impact on the value of beta 12. And if beta 12 doesn't change materially by varying the presence or absence of beta 1, beta 2, or beta 3, we get an indication of whether or not the interaction is confounded by age or gender. Okay? So there are many, again, this is really only just providing you with the fundamentals here, in a way, admittedly, pretty elaborate. But one of the circumstances that then the investigator may face is if, in fact, all of the various interaction issues are ruled out by some detailed exploration, then we are in a position to study the two exposures separately. In other words, we can now ask, is there a disease exposure 1 relationship, assume common to exposure 2, and is there a disease exposure 2 relationship, assume common to exposure 1? And that is one of the models we might wish to entertain. You can see there's still a fair bit of complicated stuff going on here now. But do keep in mind that now that we've removed all the terms involving the product of exposure 1 and exposure 2, that all of the regression coefficients in this model now with 12 terms have different interpretations compared with what they had when we did, compared with what we got when we did have the terms involving the product of exposure 1 and exposure 2. So that's only just a start, isn't it? We could then have modification seen from this joint model, jointly exploring the impact of exposure 1 and exposure 2. Okay. Further, we also have the ability to explore the extent to which that we needed this model that involved both exposure 1 and exposure 2. And like we've seen before, we are maybe going to be wondering about whether or not we could have analyzed the two disease exposure relationships separately. In other words, having a model just for exposure 1 and then another model just for exposure 2. Okay, one other point I'd like to make for you about this particular model we're looking at now, this one that involves 12 terms, is that it is structurally identical to another situation. In other words, we could have had a single exposure here with just 3 levels. Then the baseline level we might call E0, and then E1 represents the intermediate level of exposure, and E2 perhaps the largest level of exposure. In other words, this particular model, although it looks like it would be the kind that would be used for a circumstance in which we are looking at exposure 1 and exposure 2 assume common, in other words, exposure 1 assume common to exposure 2 and vice versa, it could have been used for a circumstance in which there is just a single exposure with 3 levels, E0, E1, and E2, where E0 is the baseline, and the regression coefficients here can all be interpreted in terms of differences relative to exposure 0 in this instance. Okay, and that's summarized then in this last slide on this section of session 8. So we could have had a single exposure with 3 levels. Now because of that, there is nothing that's assumed common insofar as there's only really one exposure. It's just one exposure with 3 levels. And I think you can see then that we could, in principle, have the study of an exposure that has more than 3. And then have models that involve E0, E1, E2, and then other values of exposure. Okay, so a single exposure with different levels. Now you might be thinking, once we get more than 3 or 4, should we be trying to model exposure in a quantitative way? Okay. If we can, like with a line reflecting the log of the odds of disease varying linearly with exposure, then perhaps that would be a more sensible option. So now what I'd like to do is take some time exploring the issue of a model in which there are 2 measured explanatory variables. And for our discussion here, we're going to suppose that for this display, we have interest in the assumption of linearity for both of the explanatory variables. So we're going to be presenting things in a slightly more general way. We could have one measured exposure, one measured potential confounder modifier, or we could have 2 measured exposures. Now, let's suppose for a moment, we'll get a little bit more technical maybe, but actually what we're going to be doing is mining the idea of completing the square, but now instead of it involving a parabola, we're going to be dealing with a function, a comparatively simple function of 2 variables. And repeating the process more or less in the same way we proceeded when we were completing the square with a parabola. So now we're going to think about a function of 2 variables. This could be, say, an exposure and a potential confounder modifier, both measured, and where we're interested in the assumption of linearity. Let's have a look. We might then have, at least in part of the model then, we might then have these 4 terms. Okay? We might have a term that involves the product of the 2 and a coefficient, and then the first variable, the second variable, and then a constant piece. But what I want to do now is rewrite this expression in terms of A and the product of x plus A, and that x plus capital A and y plus capital B plus capital C. If I do so, then I get this expression. And in fact, it turns out that there's very simple algebra here, that capital A is C over lowercase a, capital B is lowercase b over lowercase a, and capital C is lowercase d minus bc over a. If you're seeing some commonalities with completing the square, well, it's pretty much exactly the same issue here. What do we now have, though? We now have that we've written this function, which involves these 4 terms, as this expression plus this number. Okay. Now, kind of like completing the square, and kind of like the parabola, we can then explore the implications. Let's, for example, look at what happens if x is minus c over a. That means that all of this expression is 0. Further, if y is equal to minus b over a, then this number is 0, meaning all of this expression is 0. What does that tell us? It says that if x is equal to minus c over a, or y is equal to minus b over a, then we get a constant. That this function of two variables is this constant d minus bc over a. Maybe you might be thinking, oh man, am I ever going to need this? Am I ever going to want to use this? Well, bear with me, because there's going to be an illustration in a little bit that will help you to see this. All we've done is taken this function that involves the value of x here, the value of y here, and the product of x and y, and now written it in these simple ways. Okay. So now let's look at the four different contingencies. We've got a little more in play here, but it's not too bad. If, for example, just to repeat, if x is minus c over a or y is minus b over a, then we get a constant. And this constant can sometimes be important to our interpretation of this circumstance. What we also see is that if x is greater than minus c over a, then this function of y is a line with this slope. Wow. In other words, if this number here, x plus c over a, is positive, we get a line that has the same slope as a. Okay? In other words, we're now focusing our attention around this piece fixed for a moment, right? And the impact on the relationship between this function and y. Okay, so just to repeat, if x is greater than minus c over a, then the function that we're trying to understand is a line, and it has the slope given by this expression. In other words, it has a slope with the same sign as a. And that we can see also further that this slope increases as x increases. Okay. On the other hand, we could think of a situation in which x is less than minus c over a. Okay. Well, then we get a slightly different picture. We get that this thing now viewed as a function of y has, again, this slope, but now because this piece is negative, we see that this line has a slope with that is the negative of whatever the value of a is here. So the slope decreases as x increases. Okay? And quite symmetrically, we can see that the same observations we made about the impact of the explanatory variable x can be done with the explanatory variable y, and we get exactly the same circumstances. We get a circumstance in which we get a line with a slope that has the same sign as a, and we get another line which has a slope which has the negative sign. The same issues. Okay. Now a little bit of notation and naming here. In the literature, the values x equals minus c over a and y equals minus b over a are called the crossings. Okay? And it turns out that this function that we started with has a rather intimidating name, but it's one for which there's quite a bit of literature. And it's actually an attractive looking thing. It's called a hyperbolic paraboloid. Oh my. Well, as we'll see in a minute, it also can be seen as a saddle. Yeah, well, I'm from the West, folks. We have the Calgary Stampede here. for you folks who ride horses. Okay, we'll come back to this. But I thought I would show you a picture of a very simple situation. And that is where we have a function that I am illustrating here. It has this form here. And let's have a look at what this looks like. First of all, the crossings. If x is 0, then the function is minus 4. We're now thinking about numbers that are in the range of log of odds here, right? A log of odds of minus 4. Okay. And this value of minus 4 is the case whatever y is. Same thing is true. If y is 0, then the function is minus 4 no matter what x is. Okay. So we can see that the slopes change as one looks at lines parallel to x equals 0 or parallel to y equals 0. Oh boy, kind of elaborate. On the other hand, it's almost harder to explain than it is to see. Here's a visual that I think some of you may like a lot. And this is a perspective plot of this function of x and y, a comparatively simple one. Notice there's the value of the function, minus 4 here, and how it extends or declines. Notice the visual here showing you a function that it looks like a saddle. Hope you can see the perspective here. So this is the part that goes up here and then goes down, and then this is the part that where one's torso would sit, right? If you were riding a saddle. Okay, so there's a fair bit in play here. So that function that I wrote can be visualized as a saddle. Admittedly, not always exactly saddle-like. Yeah, I guess I did promise you saddles and crossings. Well, here they are. Okay. So you could spend a fair bit of time staring at this visual to try to understand where the crossings are and where the different features that are in play are illustrated. There's quite a bit. So if you think about x equals 0 and trace where this saddle goes, and similarly when y is 0 and trace where this saddle goes in this little visual here, you can see the issue of crossings and how this thing is saddle-like. Okay, how about we get to something that we might be able to wrap around, and that is how are we going to use this in epidemiology and biostatistics? And you may be thinking, oh, maybe Gordon's really lost it here. He's taking us miles and miles away from epidemiology and biostatistics, and we're looking at complicated functions. Well, not so bad. Not so bad, and actually quite, frankly, practical in some instances. Let's take a simple example. For example, a circumstance in which we have the log of the odds of disease, we have one potential confounder modifier that's measured, and we have an exposure that's measured. And we might think, if we're prepared to assume linearity, perhaps we would want to start with this particular model. So you would think, okay, there's 4 regression coefficients. But the challenge for you is not the theta will fit this model or R will fit this model effortlessly. It is, what do we get from such a model? How does it provide us with an understanding of the disease-exposure relationship and the extent to which it is modified or confounded by an explanatory variable x? So now what I've done is taken what we did up above in terms of the A, B, C, and D, and now rewritten it in terms of the regression coefficients beta 0 to beta 3. And we get something that is, well, it looks worse, but it's not. It is this thing that we can take with considerable advantage in understanding what this model's telling us about the disease-exposure relationship. Okay, because we get these crossings again. We get the crossing in this instance when x is equal to minus beta 2 over beta 3. And we have also a crossing of minus beta 1 over beta 3 with regard to the crossing when e is set to that value. Two crossings, one in terms of the explanatory variable x, and one in terms of the exposure e, both measured. Okay? So all of the parts to this, as I alluded to before, have interpretations in terms of the rising and the falling of slopes, the rising and the falling of lines. Okay? We see that at the crossing, we get a change in sign of a characteristic that can be important to us. The sign change. This is the crossing, going from either negative to positive or positive to negative. Okay? And it turns out then in one range of x, the log of odds increases with increasing values of exposure, but in the other range, the log of odds of disease decreases with increasing values of exposure. Now, in some literature, the extent to which we have both circumstances can be a feature that would require considerable consternation. Is it at all reasonable to have a disease exposure relationship that has those sorts of features? And the illustration I have for you in a minute should help to understand this. But it can be that if, in fact, the value of that explanatory variable where there's a crossing is outside of the range of possible values of x, then this issue of this change in sign won't be present. Now, there may well be circumstances that one could conceptualize for which the change in sign makes perfect sense. And I'll allude to that a little bit for you in the illustration. And so we have the same notion here that involves both the crossing with regard to the potential confounder modifier and the crossing with regard to the exposure. Okay? We can see that in both cases, this number that I can compute, beta naught minus beta 1 times beta 2 over beta 3, might be an important characteristic. And in Stata and other software systems, you can construct estimates and confidence intervals for this potentially important value. Okay? One of the things that I didn't mention explicitly here is that all of this discussion of crossings implicitly involves the fact that beta 3 is not 0. We're in a much simpler circumstance of additivity if beta 3 is 0. I mean, you can see here that everything that I have done here requires that beta 3 is not 0. Okay? So, again, our investigation of this disease exposure relationship might begin with the study here of beta 3. And if beta 3 is not 0, then we're in a position to look at a saddle and discuss crossings. Okay. Let's take a look at a simple example. Well, you're going to say, Gordon, this isn't entirely simple. On the other hand, setting it up is a comparatively easy process. Let's look at the study. This is from the dataset WCGS, in which we're wondering about the modeling of coronary heart disease in terms of cholesterol and a person's age. And for our purposes here, we're wondering about the circumstance in which we have actual age and we have the actual cholesterol values. You may find it instructive to have a look at this data set in some detail. and look at the values that are involved here. So what are we're thinking of? We're thinking of a model like the one I've just written up here. This one. So we have that X here is the age, and age is viewed as a potential confounder modifier. And the exposure here is, this measured exposure is the person's cholesterol level. And we're modeling then the log of the odds of coronary heart disease. Okay, so that's the context. And this is what the model looks like. So we need to first construct the product of C and A, right? That is E times X, right? In what we looked at above. And then we have this model that has only 4 terms, the 3 explanatory variables in addition to the constant. Okay. And this is what we get. And you can see that we have some coefficients here that are, oh boy, understanding what they mean. I can't just stare at these numbers and magically discuss, okay, what's going on. Now this, you might be thinking this number that is the coefficient associated with the product of cholesterol and age is tiny, but again, don't be misled here. Both cholesterol and age, when we take the product, give us large numbers. You could make the case for some centering and scaling here to aid in making the values not so tiny. That's not really material here. Now you might also quibble with me about the fact that this particular number here, while non-zero, perhaps is not statistically significant. Let's leave that aside for the moment. We're now in the world where the mighty p-value isn't necessarily the driver for all circumstances. Let's not go there. Let's take a look then at the various pieces involved. Sure enough, we can take the minus this is the minus of the coefficient associated with cholesterol divided by the coefficient associated with the product. What is that in this instance? That is our term. Going back here, we have that is minus beta 2 over beta 3. Okay, so that's this first expression. X is equal to minus beta 2 over beta 3. So we can compute that. And we get the number, pretty big number, 73. Pretty big number there, 73.88. Keep in mind that number is an age. Right? We're wondering about the crossing here. That occurs for individuals aged roughly 74, right? Okay. The second crossing, minus beta 1 over beta 3, is this number. Again, a pretty big number here. We're getting a number nearly 400. Notice this number is a cholesterol value. So there's an age, and there's a cholesterol value. Okay. And there we have the value that may be of some central interest to us, and that is the constant when either the crossing is equal to minus beta 2 over beta 3 for the exposure, or for the age, or for the cholesterol value. This constant value. And as I'm noting for you here, we can use in Stata the post-estimation command for NLCOM, which is for nonlinear combination. And we we've now got all of the essential features that we might want to understanding the extent to which the log of the odds of coronary heart disease is impacted by one's cholesterol level. Okay. So the fit ends up inevitably involving this. So here I've taken the regression coefficient, that is our B3, and here we have the two pieces, right? The two pieces that are involved here that we computed. This is the crossing in age, and this is the crossing in cholesterol. Well, it turns out that for this particular study, the range of ages that we had was individuals between 39 and 59. So the age crossing in this instance is outside the range. So the issue of the sign change for this crossing doesn't come up. On the other hand, the range of cholesterol values in these units is 100 roughly to 100 to 650, and we can see that the value of roughly 400 is in the range. So we can see then that the impact of cholesterol on the understanding of this log of odds of coronary heart disease and age depends on cholesterol. And there's a sign change here. So we could look at to what extent it might make sense that the impact of cholesterol in this case, the log of odds of coronary heart disease and age is changing in its behavior depending on the age of the individual. There's quite a bit in play here, and we're just going to have to leave that for now. If you decide you're interested in this particular illustration, you might try changing the units of cholesterol to metric, just to see what things look like, and you might find it instructive to try the centering of age and cholesterol, which we did not do at the start of this, and look at what the implications for these models are. But more crucially for us is that instead of just going back to these regression coefficients, you see in many places where people just say, well, this number is statistically significant. What does it mean? Well, we don't know. What I'm arguing for here is that we do get characteristics that we can understand, that we can provide in the interpretation section of our project, of our publication, perhaps. Okay. All these things are, at least in principle, in play. And as I alluded to, we can have quite complicated extensions to this by, for example, adding now gender to the study, in which case we now have age is measured, exposure is measured, and gender is dichotomous. Then we can get the whole issue of the study of the saddles. In this case, there's going to be one saddle for the women and one saddle for the men, and the whole study of the features of the crossings insofar as they depend on gender. So notice that the crossings and the whole discussion now involves, I would say probably to get anywhere, you're going to have to at least provisionally view this separately for the men and the women. And one of the points that does come up, and has come up in the application of this particular model, is whether or not we're getting something that actually makes sense. And if in fact the formulation or presentation of such a model leads to crossings that really cannot have some sort of any form in reality, then that says that one needs to reconsider the formulation of this particular model. It doesn't mean just immediately make it simpler and resort to an additive model, for example. That's not necessarily what's in play here. It may mean, well, we've got issues of, could be nonlinearity. Remember, all of this that we've displayed so far here is about interpreting this logistic regression model with an assumption of linearity. Okay, so we could have two measured exposures and then have notions of interaction as well. So here we've looked at the study of an analysis in which we have a measured exposure variable and a measured potential confounder modifier. But we could have all of this work that we've done here applied to the circumstance in which we have two measured exposures. Then we have the dilemma or the challenge of understanding interaction, and then positively, if there's no interaction, the impact of one exposure assumed common to the other. Okay, and just very briefly, I can point out that we can have even more elaborate models in which we have three measured variables, and in which case we have a whole range of potential ways to at least get a handle on what these models mean. There's quite a bit in play here, and I'm listing this particular last page for this section on saddles more just to point out that the circumstances can be extended. When you do that, well, things are getting wilder. And we could have then lots of saddles. We could have circumstances in which we have nonlinearity, in which case we get the notions that extend our understanding of how the various parabolae can be involved. So it's a bit on the technical, definitely on the technical side here. But again, the point being here that has been my focus, frankly, since the very beginning of these sessions, has been understanding what it is we get from a model and interpreting the pieces to it, seeing whether or not the interpretations make sense in our understanding of, well, the objectives of our project. One of the very finest series of books written for health research is the series of actually 4 volumes written by Norman Breslow and Norman Day. They're called Statistical Methods in Cancer Research, and they were published by the International Agency for Research on Cancer back in the 80s. And parts of these books may have the appearance of being rather dated insofar as some of the computer-related matters. But frankly, the careful and thorough attention that Breslow and Day give to this marvelous set of material is so worthy of your attention. And I would also draw your attention to the fact that while you can, of course, still purchase these books in hardcover, one can go to the website of the International Agency for Research on Cancer and download these books as PDF files. And that you can do so for free. And I cannot recommend these books enough. Maybe the very, very finest, for me anyhow, over the years has been the book on case control studies. And I'd like to now just take a few minutes and highlight two of the illustrations from this volume by Breslow and Day. And this one is an example that has to do with a case control study of childhood leukemia and tumors and the exposure to X-rays. A study that was done, let me see now, that was back in the early 1970s. So I cannot comment here for you on whether there's any currency to this research, but rather we're interested in taking the approach that Breslow and Day offered and giving it some attention. So you can see I'm giving you a little bit of the background that's mentioned in the book, and I'll leave that for reading. But the point being is that there's quite a bit in play here, and how would we go about attempting to analyze this information? So we're going to have involved is the identification of this disease, in this case control status by exposure, that is exposure to these X-rays, by the year of the child's birth. Okay? And what is done in Breslow and Day is they do not initially assume linearity for age here. Okay? In other words, they're looking at this disease exposure relationship for each year in their display initially. Okay? In other words, because this data was quite enriched, they were able to consider a stratified analysis where we're looking at the year of birth as a potential modifier confounder. Now, there is quite a bit in play here, but let me see if I cannot give you some of the most crucial features for this. So I have then essentially reanalyzed this data, which is available from the IARC, and then use Stata to carry out a stratified analysis of the odds ratio and stratified on the year of birth. Okay. And what do we have here? Well, it's a lot. The first thing is that there is a zero cell in the very first 2x2 table, and so we see that one of the odds ratios is excluded from discussion. However, what we can also see is that, well, it does appear that we have something more than just a linear relationship between the odds ratio and the year of birth here. Now, what we can get straight off the bat, even though there's many years here of data, is we can get a test for modification here. So we can ask, is the case status X-ray, or in this case, disease exposure relationship, modified by the year of the birth of the child? And in fact, we get a test of significance, omnibus here, of that is below the 5% value, right? So we can see then that it would appear that it would be unwise to discuss confounding here, that there is, in fact, an indication that this year variable, year of birth, is modifying the odds ratio. So you can see we're getting quite a range of values. Early on in this disease exposure relationship, quite high values of odds ratio. then perhaps declining, and then perhaps leveling off or rising again, perhaps. Okay? Lot in play. And this is a part of what Breslow and Day offered in their monograph. Okay, because what they then did was they offered the comparable model or comparable circumstance when we assume linearity and when we assume a quadratic form for the modification. Okay. So in order to do this, we need to construct then the various variables involved, the product of the case control status by year, the product of the 2 years for our analysis of a nonlinearity, and indeed the product of the case control status by the year squared again. There's this lovely double hashtag symbolism that one can use with Stata that gives you the ability to ask Stata to construct fairly complicated models with a lot of regression coefficients with a very simple form for it. I'm not going to speak to that anymore, but if you see that double hashtag in the use of this analysis, it's a quick way to get the model we'd like. However, you'll recall that we did have the issue of a zero cell in 1944, in the year 1944. Okay. So that means that Stata takes some remedial steps here and drops a particular variable because of that zero cell. Unfortunately, the default here is that Stata drops the last variable, in this case, the variable associated with the product of case control status and the year 1964. Now, maybe that makes the interpretation here a little bit trickier. So what I've done for interest here is showing you an example of reverse coding. In other words, let's redo this now with, instead of the year, we'll reverse it starting with the year 1965, and then decline the years steadily to 1944. If you do so, then 1944 becomes the last year input into that list, and it becomes then the one that's deleted, which makes more sense here for the process. Again, this is a somewhat rather annoying technical issue, but does aid us insofar as we will then be able to interpret these coefficients. Okay. And we get a lot of terms here and a whole range of issues. Maybe I'll just take a brief moment here and point out that we could try to handle that zero cell circumstance, which is displayed here, by using an exact method. And I'll be talking more about this use of exact logistic regression in a future session. But for now, we can see that we end up getting an actual estimate that was missing from the approximate analysis, or the classic approach, where we use the approximating parabolas, as I mentioned earlier. But in any case, we can get an estimate, and there's a lot been written about how or when we might want to use exact methods in order to construct odds ratio estimates in circumstances where there's zero cells. And we end up with a new notion here, something called median unbiasedness. And again, quite a bit written about this, and a comparatively recent article, too, from 2002, that details quite a bit of this important issue. All right. So that was the model that assumed linearity. Okay. Then we can redo it all again. Oh, sorry, that wasn't the model that assumed linearity. That was treating the age as an explanatory variable that determined each of the various strata, and quite an elaborate analysis. Now let's look at the two models where we use either a parabola or a line, and here they are. And you can see the simplicity we're getting straight away compared with the stratified analysis that looked at each age-specific odds ratio. Some loss of information, you might be thinking. Nevertheless, we get two panels here that are worthy of study. We get it immediately an indication that the crucial odds ratio issue here does appear to depend on age in a nonlinear way. That's this p-value here. Again, you may find it instructive to write out specifically what that means in this context. And it is indeed giving us a measure of modification, and modification in a nonlinear way. Okay. Nevertheless, for interest here, I'm including the analysis assuming linearity. And you could say, well, should I have done that given that I've displayed nonlinearity? But again, what I'm attempting to do for you is reproduce the analysis that was done by Breslow and Day. And indeed, they offer, and I've re-expressed this partially for you, but we've got the actual odds ratios on or odds on the logarithmic scale, okay, and the various images. They offer, in fact, the visual corresponding to the differences here, or the difference between the two log odds. I thought that this visual maybe is a little more informative in showing the various individual log odds estimates from the first model that I fit, essentially duplicating the stratified analysis, and then the two models, one assuming parabolic forms and one assuming linearity. And again, I would refer you to the marvelous writing by Breslow and Day on this illustration. So just to reprise, in Breslow and Day, they offer, instead of this picture in terms of log odds, this is log odds of the being a case control in terms of they offered the odds ratios. Sorry. And in fact, this visual could be taken and converted into their visual for the actual log odds ratio. All right, let's take a look at a second example from Breslow and Day's book on case control studies. This particular example starts on page 213 in Breslow and Day. And we can see here that the objective of this case control study was primarily esophageal cancer case control and tobacco consumption. That being their primary attention was, is there a relationship between case control status and exposure, where exposure here is exposure to tobacco, and the case control status is esophageal cancer. And we'll begin, as they did, with a look at whether or not this tobacco consumption can be quantified as either less than a certain threshold or above a certain threshold. And we have then the case control status coded in the usual way. And further, they were interested in this project is whether or not alcohol consumption was a potential confounder modifier. Okay. Some of the language here that I'm using is translating it into terminology that perhaps is more appropriate in this particular day and age, but I think you'll have no trouble at all with reading the discussion in Breslow and Day with a slight conversion in the language and the terminology definitions that are being used. The issues are exactly the same. Okay, so with that in mind, with a dichotomous case control status, dichotomous exposure, and dichotomous potential confounder modifier, okay, we could construct a 2x2 table, two 2x2 tables, one for the group with low alcohol consumption and one for the group with higher alcohol consumption. And what do we see? We get this set of 2x2 table. We get these two odds ratio estimates, and we get the no evidence of modification here, and no evidence of confounding. Okay, so the two odds ratios not judged to be meaningfully different, and the crude and combined after assessment of the confounding, then, in the absence of modification, we get an association then, after, whether or not we adjust or not. We get more or less the same information, right? So there is a relationship detected in this simple analysis between the case control status and exposure. Then we could look at the two 2x2 tables separately. And so here are the two individual 2x2 tables. Now, it turns out that Breslow and Day provide considerably more analysis that I'm offering here in the relationship between case control status and exposure with adjustment for a single explanatory variable. In particular, one of the things they then did was they thought, how about we will display things in admittedly a much more elaborate way, considering 4 levels of the alcohol consumption and 4 levels to the tobacco consumption. Okay, so 4 levels of alcohol and 4 levels of tobacco. The data could be displayed then, again, in exactly the same ways we did before. Now we've got, well, you could say, if in fact the issue is, again, still about whether or not case control status is associated with tobacco exposure, we've got a more complicated situation to explore. Now we've got a lot of 2x2 tables. And there's a tool in Stata that one can use called tab odds, which gives you a variety of odds ratios for the different combinations of tobacco and alcohol exposure. So if there's four levels of tobacco and there's 4 levels of alcohol exposure, we can get all of those 16 odds, right? And then all of the 16 different odds ratios with a baseline group of, say, the first here. And what do we get? Well, we still get this interesting circumstance now we can then explore whether or not there is evidence that the odds ratio depends on these various groups, and that's what they did in this instance. They took the analysis of the simplified analysis I did first for you with just the two 2x2 tables, and then looked for some indication of dependency on either tobacco status or alcohol status. And it's a rather complicated set of information they offer, and I don't propose to provide you with too much interpretation here, but will again refer you to the discussion that's in the book by Breslow and Day. Here, what I've done is, again, presented it to you using Stata to do the analysis. And indeed, the data sets are available, so you could also explore this on your own and see if you can't get that. How about then we then revisit then the extent to which we have a specific relationship between case control status, that is this esophageal cancer, and tobacco consumption, that odds ratio, right? And think about it stratified by the amount of alcohol consumed, right? So again, we're getting back to, is alcohol a modifier? Okay. If I do so, again, using this tab odds facility in Stata, I get an opportunity to reproduce some of the key pieces that are in Breslow and Day's analysis done all those years ago. Okay. And you can see we get some indication here of a dependency on alcohol consumption that perhaps we did not see from the very simplest analysis. The odds ratios here adjusted for tobacco consumption. Oh yeah, and also here what they did was they considered these odds ratios stratified on alcohol consumption but adjusted for tobacco and age. So there's quite a bit in play here. Again, I'm presenting this to you to show you that we could, in current times, reproduce what they did in those analyses all those years ago. Okay. And we could do the same thing again, where we could then think of these odds ratios stratified, on tobacco, and then adjusted for alcohol and age. And then that's what they explored and attempted to interpret. And what is also available to us, as was to them back in those early days, we could, in principle, construct a logistic regression now with the 4 alcohol level groups and the 4 tobacco groups, allowing for the possibility that alcohol modifies the characteristics. And so we can see that, in fact, we get the ability to reproduce the analyses they did. And I think what's instructive here is that back in the day when Breslow and Day were doing this work, they were interested in these complex models, not just a simple or oversimplified situation, if I may, assuming assumptions that clearly were not tractable, like, if I may, additivity, which is in 2022 often seen as the argument that's made that additivity is somehow justifiable Whereas in this work, they were attempting to drill down the much more complex issues in play in understanding the relationship between esophageal cancer and tobacco consumption. All right. To provide a wrap to session number 8, I thought I would include one more rather famous study and some analyses that were done that will provide us with yet another illustration of the use of the methods we've seen in these sessions. And this was a study collected by and conducted by the University of California at Berkeley, and it was dealing with an issue that was of concern at the time, and that was there gender bias in admission to graduate programs, and in particular, were men being given preferential treatment over women in admission to graduate programs. Okay, so if indeed it's reasonable, and indeed it is, to assume that men and women who applied for admission to graduate programs were equally qualified, and that we'll take as a given, I guess, then we would expect equal acceptance rates by gender. However, if one does a preliminary analysis of this data, a preliminary analysis might give the impression that men were being admitted in higher proportions than the women were. All right. So here's what the data looks like, and it's configured in a way that I hope you'll find familiar. We have the not admitted or not accepted into the program. That's coded 1. And then 0 means that they were admitted, okay? And then we have male, female here, okay? Male and female, okay? And then we have a number of different, this is stratified on the major that these students were applying. So we've got the indicator for not being admitted. That's placing it in a negative negative context, that you're not being accepted. And then the indicator for women. So the 1s here are the women and the 0s are the men. And then we have in this case, 6 different strata, the 6 different graduate programs that were considered here. Okay, and if we had done what we would call a crude analysis now, or simple 2-by-2 table comparing the cases, those who are not accepted, or what is this, accepted? Yes, this is now presenting the data in terms of the odds of acceptance. So the cases are those accepted, the controls are those who are not. Now we'll revisit this in a minute. Here we have the exposure. That is now let's see if I make sure I get this right. Exposed here are the males. Oh yes, here I have it here written in this variable here. So we've got case control status. Cases are admitted, not admitted, and then exposed is the men and unexposed is the women. You could say, well, let's sort of spinning things in the reverse to the way we want to see it. But let's just look at this display. Hopefully I've got this correct for you. On the basis of this 2-by-2 table, we can see that there does appear to be a relationship between acceptance and gender. And in particular, it says that it looks like the odds of acceptance for the males is estimated to be more than 1.8 times the odds of acceptance for the females, right? It does look as though more men are being accepted into graduate programs than the women. Okay, and you'll see here that I've then done this also for both the risk difference and the risk ratio, just to show you these circumstances here. Notice, by the way, that although I have presented this to you in terms of the probability of acceptance into a program, Stata nevertheless uses the terminology of risk. And so this is one of those places where I would say that it's nice to have the negative thing in being the probability of the negative thing, which is the probability of not being accepted. So here, the risk of acceptance is not a phrase we would use, right? We would speak in terms of a success rate here rather than a risk. And this goes back to, frankly, one of the very early comments I made in session number 1. Okay, let's get to the heart of this then. Leaving then things as they are, how about we stratify on their major that they've applied to? What's going on? The odds ratios very definitely appear to depend on the major that the students were applying to. And notice that it's all over the place, isn't it? The odds ratios are less than 1 in majors coded 1, 2, 4, and 6, and slightly above 1 in majors 3 and 5. Now, there's something to be noticed here, that none of those numbers are as large as 1.84, the crude. And in fact, the Mantle-Hansel combined from this analysis is actually less than 1. On the other hand, we would say, wait a minute, there's evidence that the major is modifying this relationship between acceptance and gender. Okay. This test for modification is below most commonly accepted thresholds. And so we can see that the relationship between the odds of acceptance and gender is modified by the major. Right. So the major that the student was applying to was modifying the relationship between the odds of acceptance and gender. Now, you might also perhaps note that the very first displayed major here with the very low ratio here, with the very low odds ratio and the very low risk ratio displayed here, that there's some indication perhaps that this modification might be largely attributable to the very first major coded 1. And if we were to repeat this analysis, where we, for example, exclude that very first major, then, well, maybe not too surprisingly, the evidence for modification goes away, and we don't get any clear indication of differences among the 5 remaining odds ratios. And the test of significance with 4 degrees of freedom is not significant. These 5 remaining odds ratios not materially different. Okay, if we were comfortable with this approach, what would we say here? Excluding major number 1, we might then argue for an assessment of confounding. This is something that hasn't come up before, I don't think. But we can see that for a portion of the strata, we can explore confounding. Okay, then we could say that for this particular collection of students, excluding major number 1, we have in fact an indication of confounding. What am I getting at? Well, that crude odds ratio showing a relationship that suggested that the male students were being accepted with higher rates than the female students goes away when I adjust for major. Okay? So the Mantel-Hansel adjusted here is nearly 1, showing no association between gender and acceptance. Okay. Maybe the more reasonable circumstance. The issue here is one, it's a bit complicated, but it is very definitely one for which we could interpret this as a confounding issue where there is a modification, though, if I were to compare major number 1 with the others. Okay? And indeed, if I did so either with odds ratios or with, in this case, the rate ratio for the success rate or for the acceptance rate, we get essentially the same thing. The crude and adjusted are different. The adjusted includes the null, includes 1, hence no indication that there's a relationship between acceptance and gender after adjustment for major. And if we were to repeat this analysis separately for these 2 majors, major 1 and all the other majors, in other words, if I was to group all of the other majors together, then what I get is some indication here of a difference in the odds ratio. For reasons that would require some study, that in the group of persons applying to major number 1, in fact, it is the reverse. It is the women who are receiving higher admission rates than the men are. And this I could think about comparing this odds ratio specific to major 1 and the Mantel-Hansel odds ratio specific to the other circumstances here, okay, which applied to the other majors, which was this number right here, this 1.03, and here we have this number of 0.349, and it's actually lower for the men compared to the women. And as I've noted earlier, we may find it more helpful to repeat all this analysis in terms of not being accepted so that they become risks rather than successes, or if I may. Okay, so we could then argue for an analysis of the not being accepted by gender, and we could repeat all of what we've seen here from this stratified analysis. We could repeat it all for an analysis using the models, just to see what the commonalities between the two. And in other words, understanding the issues that are in place in our nice stratified analysis we've tried, and then with the corresponding logistic regressions. And we can do that. So we'll then model the probability of not being accepted, and we'll let the characteristic, the indicator variable F for female, and then we'll have the variable major, and we have the 6 different majors. And here, in order to enable a comparison between major 1 and the other majors, since major 1 appears to be a circumstance that's slightly different, we could do that. And in which case, now the regression coefficients we get are then comparisons on the log odds scale for one major relative to major number one. Okay, so one of the non-majors 2 to 6 when compared with major 1. And what we get then is very definitely indications that would be worthy of our study. I don't want to spend too much more time on this. This session is already getting pretty long. But I can point out to you here is that we might see features here that tell us some very interesting things about the circumstances. So now we're drilling down what was before an omnibus test for modification. And it's then been made more specific to the circumstance in which we're taking major coded 1 as the baseline group. And we can then ask, so which of these log odds ratios is interesting here? And what we see, there's some very definitely features that might be worthy of some reporting here. And we could repeat all this again without major 1, and then we get another interesting set of features that might be helpful. This is now looking at the analysis of differences among the log odds ratios where our attention is restricted to comparisons between the majors that weren't major number 1. And now for this analysis, major number 2 became the baseline. Okay, whereas you can see here, and I'll leave this for your study, lots of differences being seen when I compare the majors relative to major number 1, and no evidence of differences among the majors aside from major number 1. And you could compare that with what we saw in the stratified analyses that we did earlier. There's quite a bit that is borrowed back and forth here, and I think you'll find that maybe helpful and instructive. And there's some further analyses that one could do, and I'm also for what I think you may find of interest is a return to a display that I provided you with at the very beginning of all of these sessions, and this was at a later part in session number 1, and that is a display of the counterfactuals. And I'll leave that for your consideration. Thanks for tuning in, and yeah, that's a wrap for session number 8.